Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here and hit the notification bell. You'll get notifications for this series and a bunch of other ones on our channel. Today we're doing multivariable calculus. We're in chapter 1, partial derivatives. Finally, we're at the section which is called partial derivatives. And this is not the end of the chapter. Don't be confused. There's going to be several sections after this. Once we have the definition, we're going to use them in a bunch of clever ways to investigate functions of two or more variables for the rest of the chapter. What are we going to do specifically today? We're going to do the definition of partial derivatives of a function f of x, y with respect to x and y, and then we'll do some examples. In the coming videos, we will also do the same scenarios we've done with limits and continuity. First, we'll focus on functions of two variables because we can draw the surfaces and the graphs at least a little bit, and then we'll extend that notion to functions of three or more variables. All right, we're going to do the definition of partial derivatives now. First of all, as usual, we're going to deal with the function of just two variables and deal with the partial derivative with respect to x and the partial derivative with respect to y. And then after we do that, we'll extend this to functions of three or more variables. The scenario is roughly the same. Once you have the idea of what a partial derivative is, we just can't draw these nice pictures in higher dimensions. And we'll do it here first. What are we doing with this? I'm going to do the detailed pictures, and there's a lot of moving parts, and it can be confusing at first, and then we'll show you that actually computing partial derivatives isn't so bad once we have all of the idea of what is actually going on. What is a partial derivative? What we're going to do is we're going to take that function of two variables, and then we have the graph of z technically, and that gives us a surface in 3 dimensions. If we hold one of the variables constant now, at first to do the partial derivative with respect to x, we're going to hold y constant, and then we'll do vice versa for the partial derivative of f with respect to y. So we're holding y constant. In 3 dimensions, this equation y equals y naught is a plane in 3 dimensions. This plane in orange specifically. That plane, when I hold y constant, intersects our surface, the graph of our function of two variables, in a curve gamma. And it should be pointed out, once we hold y naught constant, z is now a function of just x. We have this horrible notation where we put the y naught in there, and it's confusing for your brain at first to see, but that's now just pretend he's gone. He's a constant number, and you will only have the variable x in your equation now. If y naught is a 7, then all the y's turn into 7s, and then in your equation, there's only a function of x. That is the curve gamma. When I have the plane y equals y naught that I've held constant, it intersects our surface somewhere. That curve is the function. Gamma is f of x y naught, which we're writing as z. That is the curve gamma. Then we go back to single variable calculus, and we know how to take the derivative of a function of one variable. What we're going to now do is specifically that. Once we have this horrible picture going on, the red thing is essentially our definition. The red line now, finally, I know there was a lot of moving parts. We have a surface in blue, which is the graph of our function of two variables. And then we hold one of our variables constant, and that creates a plane in 3 space. That plane intersects our surface in a curve. That curve we call gamma is the function of now just the variable x, f of x. That function of one variable now has, in the plane, which is a copy of R2, it now has the notion of, the regular notion of derivative, and we can get arbitrarily close to there and give the ordinary definition of derivative of this function z of a single variable x. We give the ordinary derivative with respect to x of z. What does that specifically look like? Buy a pretty picture. Math is awesome. Fun math is not an oxymoron. Here we go. Partial derivatives, some of my favorite things. Multivariable calculus is one of them. Cats are another one. The partial derivative of a function of two variables with respect to, I don't like writing that out, so WRT, with respect to variable x at a point x naught y naught is, this is our notation, and again, a lot of the time when you're doing it, I'm just going to write fx. That means the partial derivative of x with, or f with respect to x at the point x naught y naught. But at first your brain is like, what's all this notation? That's just at the point, don't worry, but we have to write it in there. And again here, if you didn't have this extra coordinate, it's the ordinary derivative of this function f of a single variable at the point x naught. This is the definition of derivative. But because we're now holding one of the functions of two variables, one of those variables constant, it has to look in our horrible notation like that. But it's an ordinary derivative if this limit exists. The notation that I may also use is, again, there's going to be two notations every time. This is classically Newton's notation, and this is Leibniz. Leibniz is this? A possession of Leibniz. I'm pretty sure Leibniz actually did use this notation. I don't know if Newton actually used the subscript x. These is partial derivative with respect to x. Coincidentally, I won't draw the picture and give you the whole spiel again and derive, but the exact same thing is the same. I don't want to... Drawing the plane this way was easier, that's why I drew it this way. Drawing it this way in the picture, I don't know if I can get it, but if we hold x constant now, that plane, which is parallel to the y coordinates, is going to intersect our surface somewhere too, and then we get a curve, and then we get a tangent line, and that is going to be the definition of the partial derivative with respect to y. Let's do that next. Quickly, again, I won't derive. We are just going to reiterate the definition of partial derivative with respect to y. So if I have a function of two variables, now what's the rate of change? Essentially, we're asking in the y direction. Last time we have two directions now, the x direction and the y direction. Once we have two directions or more than one direction, we can ask what's the rate of change of that function in the direction of y or in the direction of x. We just did the direction of x. Now the partial derivative of f of xy with respect to y at a point x naught, y naught is we hold x naught constant now. So now z will be just a function of y, and then we take the ordinary derivative of that function of y with respect to y, and that's exactly what our definition is for partial derivative. Again, this is Newton's notation and Leibniz notation for the partial derivative with respect to y. Let's do an example. For our first example, example 1, we want to find the partial derivative of fx and the partial derivative of xy of a function of two variables at the point 1, 2, or 2, negative 1, sorry, dyslexia. Again, in your mind before we start, in the theory, we called it x naught, y naught. The first thing you want to do with an example, and that's hopefully good instructors, that's why we're doing the example right after, you have to take the hot mess of x naught, y naught, and all of these symbols and say, when I get an example, where is all of this stuff and what does that mean? Now this is the point x naught, y naught. And it'll be much easier in the example for you to see for the first time. Once you've seen the example, go back and look at the horrible definition again, and it will make more sense as to what they're talking about, those moving parts. Solution. First, let's find fx. What we're going to do is we're going to create a function of just x by holding y constant. Y is going to be the number -1. So we're going to let y is going to be -1 is the plane that we get. That plane intersects our surface somewhere in a curve. What is that curve? That curve is going to be z equals f of x -1, f of x y naught. He's constant now, and that gives me, I put -1 wherever y was. This will give me x squared minus x plus -1 squared plus 1, or z is a function of just x now, which is x squared minus x plus 2. Now you can see what they're saying in that general idea. When I hold y constant, that plane intersects my surface, which gives me a curve. This is gamma. It's now a function of one variable x. I can now take the ordinary derivative of z with respect to x using single variable calculus and Sir Isaac Newton's definition, which he coincidentally derives hiding from bubonic plague in isolation in 1665 and 1666. What do I do with this now? Therefore, the definition of the partial derivative of f with respect to x at the point 2, -1 is by definition, the double dots means equals by definition. The partial derivative of f with respect to x at the point 2, -1 is equal to, by definition, the limit as h approaches 0 of f of x. Sorry, what we're going to do now is x naught, y naught. But what do we have to do in our definition? Plus h negative 1 minus f of 2 negative 1 over h. Now we have all those put in there. It doesn't look so bad. It looks still pretty bad, but at least a lot of them are numbers. Now we're going to clean that up. I won't do this by definition for this guy. I'll just show you the clever trick. Once I've subjected you to this, there's a faster way of doing this. All right, what do I get from there? We have to clean this up. What is f of 2 plus h comma negative 1? That is, I put 2 plus h wherever x is, and I put negative 1 wherever y is. That gives me 2 plus h squared minus 2 plus h plus 2. This is the first derivative. It's just got the little more complication of the y value in there. That gives me 4 plus 4h plus h squared minus 2 minus h plus 2. Cancel, cancel. And then what's 4 h's minus 1 h, 3 h's. This gives me h squared plus 3h plus 4 when I simplify. Then I need also the pieces. Before you cook soup, do you just stick whole carrots and whole celery, just get in there and be a soup? No, I'm going to cut and prepare the onions and the celery and everything first, get the moving parts, then we'll put it into the machinery and stir the pot. I need now f of 2, negative 1 without the h. This one's even better. You put 2 where x is, you put negative 1 where y is. This gives me 2 squared plus 2 times negative 1 plus negative 1 squared plus 1, which is negative 2 plus 2 gone, which is 4. Those are going to cancel. Anything without an h term should cancel. You factor h out. H goes to 0. We have our ordinary definition of derivative. Thank you, Newton. And Leibniz, I guess. Now that we have those pieces, what are we going to do? I just erased the first line. I already know what it is. F of 2 negative 1 is 4. F of 2 plus h negative 1 is h squared plus 3h plus 4. Now let's use the definition of derivative. Okay, by definition, the partial derivative of f with respect to x at the point 2 negative 1 is this horrible limit, which now that we've simplified that and cut up all the pieces, now I'm going to put them into the pot and stir. This is f of 2 plus h comma negative 1, and this was f of 2 negative 1. Now notice, just like in regular calculus, anything without an h in it cancels, and we're going to get equals the limit as h approaches 0 of h plus 3 over h. Factor the h out, don't be lazy. Now that cancels, and you don't get 0, you get 1. H over h is 1. It's my favorite trick. This gives me the limit. Yes, you have to write limit every time. The limit as h approaches 0 of h plus 3, which is, now this is a polynomial which is continuous everywhere in its domain, which is everywhere, so I can plug those values in. 0 plus 3, which is 3. That's a horrible calculation for, yeah, I don't like the definition either. That says the partial derivative, not a 2 derivative, 2f. Start at the bottom for your symbol. The partial derivative of f with respect to x at the point 2 negative 1 is 3. Remember, it's a number. It's the rate of change of that function in the direction of x. All right, what we're going to do now is, instead of doing that definition, I'm just going to show you the clever trick of what we're really saying. I'm going to find the fx at 2 negative 1 and fy at 2 negative 1. The first time, instead of doing that horrible limit that I just did, all we're going to do is say what they say in all the textbooks. I'm holding y constant, and then I'm taking the ordinary derivative with respect to x, and then I put it in at the point 2, and I find the value. What do I mean by that? I mean this. Z is now f of x negative 1, which is the function x squared minus x plus 2. We already saw this. Now what I can do with that is the ordinary derivative of f with respect to x is 2x minus 1. And so the derivative of f with respect to x at the point 2 negative 1 is equal to 2 times 2 minus 1, which is 3, just like we did the long way. So this isn't so bad. And then when we have that it's differentiable with respect to x and y on an entire region at every point, then we'll get a nice quick way of calculating first or partial derivatives, and then we'll go to higher partial derivatives and mixed partial derivatives and all these fun things Claireau's through. What do I do for the partial derivative of f with respect to y at this point? I do the same thing. This time now z is f of 2y. This one we didn't do yet, so let's do this. This is, I put 2 wherever x is. That gives me 4 plus 2y plus y squared plus 1, which gives me the quadratic y squared plus 2y plus 5. Then what I do is to find the partial derivative of z with respect to y, I now take the ordinary derivative of that, which gives me 2y plus 2. And then the partial derivative of f with respect to y at the point 2, -1 is I put -1 into here and I get 0. Please subscribe right here. Hit the notification bell. You'll get notifications for this series and many others on our channel. I'm the Tutor Wizard, Adrian. I'll see you next time. Oh, we did that even in that. The picture ate the wizard. The wizard ate the picture. I don't know. Ouroboros. Mild-mannered professor by day. Super rock wizard by night. That's